Thanks for joining me today. You actually made a great choice. So this is the first time we are talking about this piece of infrastructure. So this is like an unveiling of a new Netflix original. So I hope it will be exciting. So first, just to give you an idea, how many of you are data scientists or work with data scientists closely? So hands up. OK, so good number of people here. So I guess it goes without saying that data science is a very hot area right now. There's a lot of exciting stuff happening, a lot of job opportunities for data scientists. So it's a good time to be a data scientist today. And I think it's a great time to be building machine learning infrastructure as well. So I've been doing this for a long time. I'm really passionate about building machine learning infrastructure. At the same time, I do have this nagging feeling that eventually I will go unemployed. And like this won't be needed anymore. So I think this talk here should have a best before date, maybe like over the next 5 to 10 years. So maybe this is irrelevant. I hope it will be relevant in like a 2028, 7, something like that. And the reason for that is that that there's the kind of the pendulum of computing, and we start with something that initially is a technical problem. If you go back to let's say 97 and you wanted to set up an e-commerce shop, it was a technical problem setting up all the Apache servers and racking and stacking the machines because the cloud didn't exist, and it was really a technical problem making it scale. And then over time, it became more and more of a human problem. So like if today you wanted to set up an e-commerce shop and you pitched your idea to a VC, you wouldn't be pitching it based on the idea that, oh, I can build scalable web services, because yes, you can use Google App Engine to do that these days. But it would be more about like, well, do you actually understand your customers and how do you compete against Amazon? And it's the same deal with machine learning infrastructure. This is the sweet spot in the time of in the history, like where everybody agrees that we have a problem. And I guess it's always the first step to admit that we have a problem. And the problem is that we want to make data scientists more productive. And also we want to make data scientists more productive and like just make it easier to apply machine learning to different business problems. So those two things. And like given that I know that like this is something that like the industry will solve over the 5 to 10 years, we wanted to be a bit forward-leaning at Netflix, really focusing on the problems that we need to be addressing over the next 5 years. And I feel that those are like more on the human side of things. Of course, your mileage may vary. And your company, it might be more technical in nature. It might be about scalability of machine learning models. It might be about lowering the latency for real-time predictions. And those are all like good and valid problems, and I'm actually happy that there are many companies solving these problems for us as well. But by and large, for most companies, these issues are becoming human issues. And hence the title, Human-Centric Machine Learning Infrastructure. And before coming to Netflix, I used to work at startups for a long time here in San Francisco and building machine learning infrastructure. And so hence I want to start with the startup story. So this is called Caveman Cupcakes. Imagine it's an amazing startup. They make these gluten-free, paleo, vegan, sugar-free cupcakes, really good for you. And here's the founder, and the proud founder of the Caveman Cupcakes. And he has learned that data science is really, really important for success of any startup, any company these days. So the founder wants to go ahead and hire a data scientist. And now imagine that like he gets a referral that this amazing person, amazing individual, Alex. And Alex is this full stack, old school data scientist who can do everything from low-level coding all the way to writing academic papers and anything and everything in between. So he gets hired. And the first problem that the founder wants Alex to solve is to come up with the dynamic pricing model. So it happens that the market for cupcakes is really competitive and the margins are thin, so they really need to optimize the margins, so come up with the pricing model. And now, well, as always in data science, we can make some silly assumptions to make math easier. So let's just say that the optimal pricing model can be represented by one single Gaussian. It's a silly assumption, but let's go with that. And now Alex starts thinking about the problem and like asking around and collecting some data and doing some like prototyping in a notebook. And he comes with an approximation, the black line here, that's pretty close to the optimal pricing model. And now he's able to come up with the good solution, and he makes an implementation in C++. So he also is a good software engineer, so he can do this in C++. And they deploy this in production, and the results are great. So they're able to increase revenue by 15%, and the founder is very happy. And now, as it oftentimes happens when you make something really successful, people come to you asking for more of the same good stuff, and now the founder comes and asks that, can you predict churn as well? So at some point, people stop eating cupcakes, and they want to prevent that, okay, people shouldn't churn. So now Alex thinks about the problem, and he realizes that the churn problem is pretty close to the original pricing problem. So not exactly the same, but close enough that he's able to take his existing solution, the solution he wrote in C++, and generalize it so that it covers both the use cases. So he's a good software engineer, so he knows that he wants to build these generalized solutions. So he builds something that covers both the use cases pretty well. So he extends his code and deploys it to production, and the founder is, again, very happy. They are now able to prevent churn really effectively as well. And now, again, there are more and more requirements. So the next thing the founder asked Alex to do is that now that our foundational business is really in a good shape, so we want to expand, so we want to spend more on marketing. So can you come up with an attribution model for marketing? And now this challenge is that first, Alex isn't an expert in marketing, so he needs to read some literature and understand what people have done in this field, but also the problem is quite different from the two other problems that he solved previously. So now he really, really wants to generalize his really awesome piece of C++ to all these problems, and he tries to come up with this solution, but it's kind of a watered-down version, and also he just didn't understand the problem well enough. So now when they deploy this in production, the results maybe aren't that great. So now imagine that instead of hiring Alex, the founder would have done something different. And in this case, instead of hiring a single individual, he would have hired a team of specialists. Maybe one of them has a PhD in economics, and maybe she's really great with pricing models, and another person is really good with marketing, and a third person is really good with, I don't know, churn models. And now when the team of data scientists sees these problems, each one of them has the domain expertise to come up with a really good solution for each of these problems. So they get really a good version, like for the attribution problem, they get a good model for the pricing and so forth. But now what is likely to happen is when you hire specialists, data scientists who really know these fields, they might not be experts in software engineering. So it might be that they have used R, like we heard in the previous presentation. R is an amazing language for doing data science. So it's a great choice, and by all means, you should be using R, let's say, for the pricing model. And the same thing with Python. Python has an amazing ecosystem, so it would be silly to say that you can't do this in Python. But now it is, of course, possible that these solutions, when it comes to software engineering and DevOps best practices, aren't quite as great as with what Alex wrote, who had a lot of experience with production systems and so forth. So now if we compare these two different approaches, so we compare Alex to the team. So the problem with Alex was that the code was great and the models were actually pretty great. Well, he didn't quite understand the marketing domain well enough. But it was all around great. But it was obvious that as the business scaled and as the problems became more diverse, his limitations started to be obvious. So you can't scale a large organization based on these unicorn, amazing individuals. And it's just not a good idea in the long term. And then when you have a team, you can afford hiring a team of specialists who really know these fields and overall are really strong data scientists. But then it might be that they don't have the software engineering background to make the solutions maybe production ready. And this is probably something that most of you hopefully feel that is pretty natural and happens oftentimes. And this has happened many times. Again, going back to the example of web services, this has definitely happened before. That we start with some technical field that requires really deep understanding, low-level coding, and then over time it becomes a higher and higher level activity. And now data science is definitely moving higher and higher up in the stack. Well, we do have this operational issue that how do we operate these things in production? And one way how historically we have solved problems like this is that we just provide high-level abstractions. So we just provide some amazing machine, let's say, data science machine that hides all the nitty-gritty details of how you do distributed computing and how you optimize your models for GPUs and SIMD and so forth. And then as long as you are operating this machine, then all is taken care of, all is good. And now your data scientists, all they have to do is to work within the constraints of the machine, and it takes care of everything for you. And now in the context of data science, like there are attempts to make such machines. So it could be Spark, it could be TensorFlow, it could be RStudio. Many attempts to do that. And of course, well, I mean, if you ask them, it might be that they are not like trying to solve everything, but kind of the mindset is that like, well, as long as you are working within the constraints of the machine, everything is good. But at Netflix, one challenge that we have seen is that when you have a very, very diverse set of problems, we are not just talking about one or two, or maybe not even three different data science problems, but you want to apply machine learning and data science in every single area of your business. It's very, very hard to have a single abstraction that works for everything. And as software engineers, we have, of course, like all seen this happening many times in different areas of software engineering, not only data science, that there are many, many promises that like if you use this framework or if you use this system, it just magically solves all your problems, and it never works. And hence, if you take a different mindset, that instead of like putting your data scientist to work on this data science machine and like say that, well, this is all you can do, you can take an opposite viewpoint. That what if you have a total freedom? You can do whatever you want, absolutely whatever you want, total freedom. And I don't know if you saw yesterday a talk about like the microservice lesson learned by Google, and like the presenter had Ben Siegelman, I guess he was his name. He had an excellent example of like having ants and hippies. I guess this would be the hippie version of things. So you do whatever you want. And it kind of sounds great, although like the presenter yesterday pointed out, I mean, there's a heavy tax, and especially as the organization grows, there's a heavy tax when you let people do whatever they want. So of course at Netflix, there are like a few things that are kind of given. So for instance, if you are a data scientist at Netflix, we think that you should be probably using Netflix data at least. You don't come with your own data and say, oh yeah, no, I mean, I'm here and this is my first day, and by the way, I'm only analyzing my own data. So you get Netflix data from the Netflix data warehouse. I haven't met a single data scientist who wants to design their own data warehouse. So the data is in S3. I mean, yeah, I'll be using that. In the same way, there have been two data scientists who have said that well, they would like to build their own machines so they get exactly the GPUs they want. But most people, they are just happy to get the compute resources off the shelf. So you say that I want 400 gigs of RAM, I want 2 GPUs, and where they come from, I really couldn't care less. I mean, it comes from the cloud, whatever. So compute resources are given. Well, now when you have data and you have compute resources, the next problem is that, well, you can't just like push stuff to the, let's say, some magical cloud and expect that everything works. So you need some kind of a system to orchestrate the jobs and like maybe execute the thing every day and so forth. So you need some kind of a job scheduler. Not very interesting maybe in a data scientist point of view. So again, most people say that, sure. I mean, I thought that that's easy. So I mean, let's just assume that we have a job scheduler. Now, versioning is a funny topic. So it's like, you know that they say that you should be flossing every day and you should be eating broccoli and like all the vitamins and so forth. Everybody knows that you should be doing it, and still it's actually not that exciting. In the same way, all responsible data scientists know that they should be versioning their code, they should be versioning their notebooks, they should be versioning their experiments, and maybe they even should be versioning their data. And again, no one does it since it's just not easy enough. And again, if a magical versioning theory came to you and said that, yes, I mean, we will just version everything for you automatically, yes, people would be very happy. No doubts about that. Now, again, this is another thing that people just think that, yes, sure, it's given that you are not an island, you are not a single data scientist, you work as a part of a team. There are collaboration tools like Slack and maybe Bitbucket, GitHub, so forth. So again, sure, people very much agree that these are good ideas, and no, they don't challenge that we shouldn't be using these. Now, getting to a more sensitive area, you know that at some point you need to deploy your models. And if you are a data scientist coming straight from academia, it might be that you have never deployed a model in production. You have written papers, you have created prototypes, you have run experiments, but you have really not deployed models in production. And if you imagine a large company like Netflix, and probably it applies to many of your companies as well, deploying anything to production is a non-trivial undertaking. So again, if someone says that we have this CI/CD system that helps you to deploy something in production, people generally are pretty happy with that. Although how you exactly deploy and like how do you monitor your models is somewhat data science or the model-specific question as well. And now moving higher up in the stack, we come to the question of feature engineering. And many of you who may have followed like news and articles about data science. There's every now and then these articles that say that 80% of data scientists' time is spent on data munching or data transformations, and it's usually said in a pretty negative tone, as if it was somehow a secondary activity in contrast to something that's supposedly more awesome. I don't know, maybe modeling. I feel personally that this is really an area where data scientists can like really give a lot of value add to businesses, understanding both the business domain as well as the models. So I think it's valuable. But there are good examples of infrastructures out there like Uber's Michelangelo. I believe that there's a talk about that later today that show that like providing features as a service, can be pretty useful as well. And then finally, we come to the question of like the actual modeling activity, so ML libraries. So is it so that like the company should provide you, let's say, 5 different models, and as long as you are using one of these deep learning models, or maybe one of our implementation of random forest, then you are fine? Or should it be so that you can choose to use whatever you want? And now how we feel about this is that if you are a data scientist, you probably should care quite a lot about the ML libraries. After all, that is your domain of expertise. And maybe you should care about feature engineering, and to a degree, maybe you should care about model deployment. But as we move downwards in the stack, it's understandable that, well, maybe you shouldn't care so much about it. And after all, you have limited amount of cognitive bandwidth, so you should focus your creative energies there on the top of the stack rather than the bottom of the stack. And then my team is an infrastructure team, so we view ourselves as a very complementary team to data scientists. So we should be caring about things that the data scientists don't care about. And then correspondingly for things, although the name says machine learning infrastructure, which is kind of paradoxical that we actually want to avoid doing machine learning, because that's what data scientists do, and like we focus on infrastructure. That's why we want to care about all these other things. And then of course over time, like we do want to provide good tools, good opinions, paved paths for doing this. Things like model deployment and feature engineering, but by and large, that should be the domain of expertise for data scientists. So most of the things that you see here on this slide are related to building models. And then there is the question of deployment. And how do you actually, after you have built something and after maybe you leverage the existing platforms to build something, how does it actually start producing business value? And that is really the hard part, that like, although everybody says that machine learning is amazing and it is the new oil or whatever, the fact is that it doesn't have absolutely any value unless it is connected to some existing business processes and the business is ready to consume the results. And that is really, when we say deploy, we don't only mean deploy in the sense of just like running it on a daily basis, but really is there actually someone in the business who can like change their like business decisions based on the model? And that is hard. And it's hard because of technical reasons. As I mentioned, like just the operating things in production is non-trivial. But also it's hard psychologically. So there's the old saying that says that no plan survives contact with the enemy. And we can extend this to data science by saying that no model survives contact with reality. So you're a data scientist, you have been building your amazing model like in a notebook for 2 weeks, and you're super happy with it. It's beautiful math, and the test data works great, and the cross-validation gives really promising results. And that's the happy phase. That's the happy part. That's the part that you really enjoy. And you have the nagging feeling that there's a chance that once you deploy it to production, the results aren't that great. And if you have any kind of technical excuses for not pushing it to production, there are like many convenient reasons just to kind of stay in the happy la-la land and keep like just iterating on the theoretical model and avoid that like humbling moment that your baby just doesn't survive in reality. So what we want to do is that we want to remove those roadblocks. We want to remove the excuses for not deploying. So putting these two things together, what we want to do as a machine learning infrastructure team, we want to help data scientists to build models, especially focusing on the parts of the stack that are not that are not that interesting for data scientists and that are not in their core domain sphere of expertise. And then we want to help them to deploy so that we actually get some business value out from the work that they are doing. And also they get to actually start working on that exciting part, which is that, well, it really, really works. It just doesn't work theoretically in my notebook, but it really works in production. So that's giving you like a broader kind of a philosophical context why we are doing this and like why we are thinking this in terms of being human-centric. And in the game and cupcakes example, I told you that there were 3 different business problems. So there was the pricing, and there was the churn, and there was attribution. Now you can imagine that as the company grows, as the company becomes more like Netflix, like this really ambitious global company that's growing fast, the appetite to apply machine learning goes through the roof. So on Monday, you may have seen Justin's talk about multi-armed bandits and how we can use it to optimize artwork. Like when you log into Netflix and you see those titles, you know probably that it's driven by a machine learning system. They are personalized, and we have a really mature recommendation engine for doing that. And that's great. That's kind of the crown jewel of Netflix. But then at the same time, it's kind of a tip of the iceberg. So there's so much that's happening behind the scenes that not many people know about. So many of these things are like, this is like only for you, my friends, that this is like amazing amount of machine learning that's happening behind the scenes that not many people know about. So there are super exciting topics for machine learning, like analyzing the screenplays, the textual content of the screenplays to understand if there will be demand for a movie or like a series like this. Or how do we actually, when Netflix is producing originals, how do we optimize the production schedule so that like everything happens at the right time? So it's really a complex operation when a movie is being made. Or overall, like when we are licensing content, how much we should be paying. All those decisions are driven with the help from machine learning models. And then there are things that are more operational in nature. Like, you may know that Netflix operates one of the biggest content distribution networks on the planet, the Open Connect devices, and how we place titles on the cache of these devices also can be determined with the machine learning model. Or how we actually operate our platforms. We can make intelligent platforms by really understanding the usage patterns. Or like when you are streaming something, what should be the optimal bit rate depending on your network conditions that are, of course, highly volatile. It could be a machine learning model. And obviously, there are things like fraud detection, analyzing marketing. It's literally hundreds and hundreds of problems that we are trying to solve using machine learning. And now, this may give you some understanding and like that why we feel so strongly about giving our data scientists freedom to choose the models that work best for these different problems. Because as great, let's say, as deep learning has become over the past years, it is a stretch to say that we could solve everything using TensorFlow. Or it is a stretch to say that we could solve these problems using any single model. So it very much makes sense to give people freedom. And it very much makes sense then to have infrastructure that can support that freedom. So now, besides all those different problems, data science, interesting challenges that we have, Netflix is, of course, especially in this conference, I am sure that maybe some of you have a drinking game about like Netflix presentations and like how often like these different things get mentioned here. So Netflix is very well known for having a very mature infrastructure and mature platforms for many different use cases. My team works as a part of the data platform organization. So this is a bit like a data platform-centric point of view. And for instance, Netflix probably was one of the first companies really starting to leverage this idea of using Amazon S3 as a data lake. So all the data goes to Amazon S3, and then there are different systems to query data from S3. It works really well for us. And on top of S3, we use different query engines like Spark and Presto and so forth. And then as our container management orchestration system, we have this project called Tidus. I believe that there was a talk about that yesterday. It's open source. But you may have heard of Kubernetes in the same space, works kind of the same way. So if you think this stack in terms of your company, probably you have some kind of a data lake or data warehouse. Probably you are using some query engine like Spark or Redshift or Presto. You may be using some container orchestration platform like Kubernetes. And then on top of that, you most likely have some kind of a job scheduler to manage, let's say, ETL pipelines or something of that sort. And like Airflow is really a popular tool for that use case. We are using a system called Mason. There have been a few presentations about that. If you're interested, there was one at the AWS re:Invent last year, so you can find it online. And then finally, on top of these foundational pieces of infrastructure, we have our notebook infrastructure. And there was actually recently 2 really great blog articles in our tech blog about how we run all the ETL pipelines, really like key pieces of infrastructure on top of Jupyter Notebooks. And we are contributing to this open source project called Interact. That's a kind of a nicer version of Jupyter Notebooks. And now, inside these notebooks, if you're a data scientist at Netflix, you can then like do whatever you want. So you can use any ML libraries, you can use TensorFlow, XGBoost, and so forth. So I joined Netflix a little bit more than a year ago, and this was the situation. This is what I saw like when I came. And looking at this, I was thinking that there is nothing to be done. I mean, they made a mistake hiring me, since technically everything is possible already. So if you wanted to run distributed TensorFlow, it's actually like quite doable using Tidus. Or if you want to use Spark MLlib, I mean, there's really mature Spark infrastructure. So there's really nothing that's needed. Technically, everything is possible already. But the challenge was that nothing was kind of easy enough for data scientists. So there was data, there was compute, there was like prototyping, you could build models, but doing this wasn't really as easy as it could be. And I can tell you a funny story. Well, I don't know, maybe this is not a funny story, maybe it's a sad story. But I mean, I was involved in this project, and it was really a great project. It's still running. So we had a data scientist who had this idea that we want to analyze the tweets, what people are tweeting about Netflix. So it happens that like Netflix has really active Twitter accounts, and understanding how people react to different shows and what's the sentiment about different shows. It's really useful knowledge for us, so that we can make sure that like we are not producing stuff that people don't like. So also a nice thing about tweets is that they are pretty short. So I guess it's like 160 characters or something of that nature. So even if you had 1 million of them, it would be just maybe 160 megabytes. So you can have it in a data frame, in a pandas data frame, in a notebook. And then you can take an off-the-shelf NLP library. There are many of them these days. I think we use Gensim for doing topic modeling. And we applied this in a notebook. And it's really like a school book example of like really awesome and fun data science. So nice data frame of real-world data and like really nice models, all looks good and fine. So this was really fun, easy part. Well, now the first realization after building this notebook was that, well, actually we don't need only a single model, but we do want to have kind of slightly different models for different cohorts of titles. So we needed multiple models. And instead of trying to train all of them in a single notebook, we want to farm it out to Tidus, the container management platform. And now, the thing is that this shouldn't be too hard. So there's actually a Python client for Tidus. So pushing stuff, running these containers on Tidus shouldn't be really too hard. And it wasn't. So the data scientist was able to do this maybe in a week or so. Well, now a challenge was that the original notebook version used Presto to fetch the data, like from the data warehouse. So there was a single SQL query that got executed. And now, when you had 100 of these models being built in parallel, a challenge is that you have now 100 queries going to Presto, and obviously they get queued up, and you won't be getting the results as fast as you got in the single model case. So it was a bit slower than what we wanted. And now, I mean, working with the data engineer, like we were able to kind of organize the code a bit better, so we were able to ingest the data a bit faster, even to these parallelized models. Well, now we had the models being built, and the data was flowing. So the next question was that how do we update this thing daily? So obviously, we want fresh results every day. Twitter tweets are real time, so the faster we can update this, the better. So now we do have this job scheduler, so we want to use the existing job scheduler. So, and there is plenty of documentation and examples how to do this. So the data scientist was self-sufficient enough to learn how to do this and like push the thing to job scheduler. It maybe took like 2 weeks to figure it out and like a few iterations, but again, I mean, quite doable, thanks to all the existing infrastructure. And then, interestingly, this was maybe the hardest part of the process, that once we had the models updating daily and like everything was good, but I mean, now you had these model files somewhere in S3 and you got the new one every day, but they were like really not doing anything good for anyone. So we wanted to start exposing the results to the business stakeholders. And we realized that in this case, the easiest way to do this is through a custom UI. And in order to create a custom UI, you need a front-end engineer. You need someone to build the backend for the web application. And, well, you still need the data scientist to help with the model. And we also had the data engineer to help with the data pipelines. So we had 4 people, plus the business stakeholder now to eyeball the results and say that if it's useful at all. So we had 5 people in the meeting going back and forth, like whether it should be modified. And like we kept iterating on this. And now, altogether, like kind of taking this project like from start to finish took about 4 months. And now if you think about it, that this is really actually like if I had presented you this maybe 10 years ago, I mean, this is pretty fancy stuff. We are taking like real-time tweets. We are building natural language processing models, understanding the sentiment of these tweets. We have a custom UI. The models update daily. It's a pretty non-trivial thing. So in that context, in that light, 4 months isn't that bad. If this was a startup and you did it in 4 months, well, it's really like not too shabby. But still, there was the nagging feeling that this could have been easier. So each one of these things kind of required the data scientist to learn about all these tools. And like, as an individual thing, nothing was too hard. But I mean, as a kind of holistically, as the whole project took a bit too long. And it wasn't only about time. But now, if you look at the code base, 60% of the code was related to infrastructure, and 40% was about data science. And now, as software engineers, of course, you think that, well, if the code is architected well enough, I mean, you have the infrastructure part there, and you have the data science part here, and it's still pretty readable. But remember that the data scientist who did this might not have been a really like a professional software engineer, so it maybe wasn't as well architected. Also, it was a pretty organic process, so it wasn't like a perfectly designed upfront. So now you have this like code that 60% something that's not data science. It took 4 months, and then there was the feeling that this could have been easier. And actually, the worst part was what happened when we started actually using this. And that was really like when the hard questions started coming in. So now suddenly we were wondering that, well, I mean, the business stakeholder was saying that, do these results make any sense? This look pretty strange. And well, now, I mean, we obviously need to monitor this model in production. That is it actually converging? Is the model even working correctly? And then one day it failed, and the data scientist was that, well, yeah, now I mean I have the red light in the scheduler, so what should I do? And how do I test this locally? And how do we debug it? And then like when we had another data scientist who wanted to contribute something to this project, there was the question that, yeah, you can take this project, but be careful not to run it because it might overlap with the production. And well, I mean, it's hard to experiment with that. And then once we fixed the model, there was the question that how do we backfill it, like historical data based on the fixed model? And after having few of these experiences, we had realized that, yes, we are indeed missing a piece of infrastructure. And this piece of infrastructure is a bit meta, and hence the name Metaflow, in a sense that it doesn't do much by itself, in a way. It just glues together all these existing pieces of infrastructure, all these solid foundational components that Netflix already has. And probably your company has as well. I mean, you probably have S3, you have probably Spark, you may be using Kubernetes, maybe you're using Airflow. So it is actually a pattern that you can replicate at home. And now if you think about this, we didn't want to build a data science machine. We didn't want to say that we are building this machine learning infrastructure, and as long as you are just using like the Metaflow API, you don't have to worry about anything else, and like we just magically make everything work. We didn't want to take that mindset since we knew that like given the diverse set of problems that we have, it's not going to work. But instead, what we wanted to do is really do, I mean, in the previous presentation, we had really good examples of the design thinking. So we really took this very user-centric design approach that, well, we don't want to hide these pieces of infrastructure by itself, but it's more like to think them as ingredients. So if you go to a fancy restaurant and you get the plate, on the plate you may see that you have a piece of asparagus and you have a piece of like a nice chunk of fish and like maybe some squash or whatever. And you can recognize these pieces. But somehow the kitchen, the 2 Michelin star kitchen, did some amazing value add on top of it that now suddenly it's like worth 100 times more than each of these pieces of ingredients by themselves. And that's kind of the mindset. So we don't want to hide the details. We want to make it easier to navigate this complex landscape of different pieces of infrastructure and just do a bit strategic value adds here and there so it's easier to run data science on this infrastructure. So I want to spend the rest of this talk like talking about what we actually did. So you probably are interested, so how does it actually work in practice? So as I mentioned before, there are 2 main activities that we want to support. One is build, the other one is deploy. So let's start with build. It's like taking the very high-level approach at first. This is like good starting point for data science. You assume you get some input data, you perform some computation, you produce some output data. And you can trivially model this as a function, let's say in this case in Python. So you have a function, it takes some input, it performs some computation, it produces some output. And now, obviously, you can run the piece of Python code on the command line. It's simple enough. And we assume that if you are a data scientist, you can do this. It's not too hard. There are plenty of examples out there. And now, when you actually extend this example here to do something practical, what happens is that instead of having one line of code, you may have 500 lines of code, or maybe you get 1,000 lines of code. So now you have your maybe train function, or maybe your score function, and it's 500 lines of code doing its thing, maybe in a notebook. And now when you have one function that's 500 lines of code, there's the inevitable question that, well, probably it shouldn't be a single function. And then there's the question that, well, I mean, should it be multiple modules? Should it be multiple packages? Should it be classes? Should it be something else? And what we say is that, well, let's make it a DAG. Let's make it a graph. And like, modeling data science workflows as a graph is nothing controversial. So this is what TensorFlow does. This is what many other frameworks do. But this is a bit at the higher level. So the idea is that you take your 500-line function and you split it in parts so that each of these steps in the graph do somehow one logical, like a piece of your computation. Like in here, we could start, we maybe fetch some data, and maybe A like runs one version of the model, and B another one, and then we compare, like, we choose the best model, and so forth. And how we do this is that we want to stay really out of your way, and so hence you can just take your existing Python code and like just add some few annotations. So you add this step decorator, and it becomes a node in the graph, and then you specify the transitions using the self next. So simple enough. I mean, going from your original notebook version to this, it's really not too hard. And then you can run it locally in the same way as you did before. So if you have ever run Python code before, going from your old way to this, it's really, really easy. Well, that's with the caveat that you actually use Python. So we do have a good number of people who use R. So what we did is that we provided the same functionality for R as well. So now if you are in RStudio, you can define your graph in RStudio, and you can run it in RStudio, or you can run it on the command line using RScript. And the nice thing about this is that we didn't have to re-implement the whole thing in R, but R is kind of sitting on top of Python thanks to this amazing library called Reticulate. So R calls Python. It's kind of high-level languages stacked on top of each other. So in a performance point of view, you might think that it's a nightmare. But in the productivity point of view, it's actually pretty useful. And now, just to motivate you, that if by now you think that, well, I mean, this seems so trivial that I'm not interested anymore, just to trying to keep you awake a bit, people actually do use this. And since we started, we have now 134 projects like using this framework at Netflix, and people are really happy using it, and the adoption seems to be pretty healthy. And it's not because you can write DAGs. That's table stakes. But there are a few other features that are really useful. So here's another one. It's really like one of the features, small thing, but I'm really proud of it. So I used to use Luigi. I don't know if anyone have used Luigi before. It's another one of these open source DAG schedulers by Spotify. I really like it. It's similar to Airflow. And what we ended up doing at my previous place with Luigi is that we run some computation, and then in the end of the computation, we sort the result in some data store like S3 or a database. And then in the next step, we fetch the result from S3 or a database, and then perform some additional computation and store the results again. So all these steps ended up having some amount of boilerplate related to persisting and loading results. So here, we wanted to make it easy enough. Just as a convenience feature, what we do is that we persist everything. So when you assign something to an instance variable in your Metaflow Python code, like here self.x, we persist it automatically after the step has finished. And there are a couple of nice side effects when we do this. One is that this, in fact, becomes a snapshotting feature or a checkpoint. So, and what that means is that now we can provide this resume function. So imagine that your start is some like a data loading step, and it takes 2 hours to run. And now B, you actually train your model. And now B fails, and you want to iterate on B, so you don't want to wait on start for 2 hours, so you can just resume from B. And this works because we have persisted the whole state of start. So we can just continue from B without having to re-execute start. And another surprising benefit of this small feature is that there are many frameworks out there that allow people to choose to persist something. And the thing is, really, the hard part is about choice. So what we saw before, like when we gave data scientists freedom to choose to persist something, is that people tend to be very conservative. They are conservative, thinking that, oh, I don't need this piece of data. I only need my model, and I don't want to do this because I don't want to add another like 100 bytes to Netflix's S3 bucket. And the challenge with this mindset is that the next day, when your model fails, and you really don't want to spend any time debugging it, but you knew that if only I had that one piece of information, if only I knew the intermediate state, the debugging would be so much easier. And that's not possible because you decided not to persist it. And we make your life easier by saying that don't worry about it. It's a drop in the bucket. And by the way, it's all content addressed. So it's all deduplicated. So it's actually not adding that much overhead at all. And we just persist everything. So we get the snapshotting. And also we get like full visibility to the internal state of the modeling pipeline. Super useful. Now the next question is about scalability. So maybe many of you looking at Python and R. So I mean, it doesn't scale. Well, yes, Python and R, they kind of are pretty high-level languages by default. Often I'm super inefficient. You could always implement like Alex in the beginning in C++, and it would be 1,000 times more efficient. But then on the other hand, like if you look at what AWS is providing these days, or Google Compute Engine, you can get boxes with 400 gigs of RAM. You can get boxes with 200 gigs of RAM. So instead of saying people that, yeah, what you did is maybe working, but I mean, it's so slow that we can't execute it, we said, whatever. I mean, let's just take a big box with 200 gigs of RAM, or maybe 16 cores, maybe a good number of GPUs, and let's just make it work. Let's rely on vertical scalability as much as we can. And all you have to do is that you just decorate your step by saying that this function requires this much memory, or maybe this TensorFlow training needs this many GPUs, and you just run it locally as before. And we farm these functions then to Tidus, and Tidus gives us the machines with these requirements. And it's very convenient because now just by adding a single line of code, you can run your idiomatic R training, or you can run your idiomatic Python training, which probably isn't optimal at all, but it's just super easy and productive. Another really nice use case is that oftentimes you don't know the graph in advance, but you want to do some kind of a fan-out, a dynamic fan-out. The typical use case in data science is hyperparameter search. So you have different parameterizations for your model, and you want to run all the models in parallel with different parameters, and then you just want it to happen for any number of models. It can be really a large number of models. So we provide this simple Python iterator, like here the grid. We say that, OK, do a for each over the grid, and then it does the fan-out. Easy enough. And one of the best proofs that people actually find this useful is that 40% of the people who use the system, or projects who use the system, start using this feature right away. And others, they first test something locally, and then when they know that they run out of resources, or maybe on their like sandbox environment, they decide that, OK, now I want to start farming out computation elsewhere. Then, as I mentioned in the NLP use case, the challenge is that when you start doing these fan-outs, you need to get data somehow. And I mentioned that we used to use Presto. But the challenge is that then running these big SQL queries many times in parallel is very slow. So instead, we provided this really fast data pipeline that goes directly from S3 to EC2. And if there's anyone, by the way, from Amazon here, they should fix their S3 transfer class in Boto, which is way too inefficient. So we wrote our own, and now you can actually get 10 gigabits per second between S3 and EC2. And you can imagine that this is a game changer for data scientists who now can do a select star in a big table, get all the data in their model, do feature engineering in the pipeline. It's faster than, let's say, in Spark, even though you are doing dumb, simple Python. And I think kind of in the interest of time, I think I will skip this slide. But the idea is that like we had a really successful project that was using R. And using these features parallel for each, we relied on vertical scalability. And it worked really nicely. And more about deployment, like since I still have a few minutes. So this is about versioning. So now versioning is one of those things that's super important. No one wants to do it. We do it by default. As I mentioned, we are snapshotting data. We also snapshot the code, and largely we want to start snapshotting the whole environment where your code runs. All these artifacts are immutable, so you can refer to anyone else's artifacts or like your own. And there are two big benefits when you do this. First, you can experiment freely. You can take any existing piece of data science code and you can start running it because you know that it runs in isolation. You can't step on anyone else's toes. You can reuse someone else's previous results and you can start building on top of that. And the second big benefit is reproducibility. So now that we are snapshotting all these different things, we can take an existing version of the model, rerun it again, and like see that we get the same results. For operational stuff, Netflix has this amazing hairball of ETL pipelines, and it used to be so, as I mentioned, when you wanted to get something in this official production scheduler, it required quite some work. And we wanted to take that pain away so that there are no excuses for not deploying to production. And now there's a single command that can take your local DAG and deploy it to production with this scheduler that then provides you operational support like reports for SLAs and alerting if something fails and so forth. And as a result, now based on our statistics, 26% of projects deploy to production. And this is a good number. It's supposed to be a funnel. This is experimentation after all, so that number should never be 100%. So we think that is a good number. But even more importantly, now the median time to first deployment is 7 days, compared that to the 4 months that it used to be. And this is so important because, as I mentioned, most of these models, if not all of these models, initially fail in production. So it's important that you see that first failure as soon as possible so that then you can go back to the drawing board and start fixing it and actually make it work in the real life. And then once you have the thing running in production, you need to know that it actually works. You could have a custom UI. We could provide a UI that shows some model metrics and whatnot. Again, the challenge is that it's very hard to have a universal UI. So instead of having a universal UI, we decided that data scientists should be able to build their own UIs. Well, now, data scientists don't want to use React. They don't want to use JavaScript. They want to use the tools they know. So we allow them to do this in notebooks. So thanks to the fact that we are persisting all the intermediate state, you can, for instance, peek into the, let's say, RMSE of a model, and you can plot how well the model converged, or you can plot some other metrics that make sense for your model. You can have the notebook run every time your model runs, so you have always a good report, good understanding, like what the model did and how well it worked. And then lastly, the previous examples I showed you were mostly about the batch scoring and batch training use cases, but obviously there are many real-time use cases as well. And for that, we provide the hosting platform, so you can run your models as usual using this platform, and then you can deploy it to our hosting service. And instead of you having to write a custom backend and a custom microservice, you just define a simple Python function, so almost like a function as a service, that takes your model, takes the request, and you decide how you want to produce the response. Oftentimes, it might be as simple as a dot product, but in other cases, it might be something more complicated. And then you get a first-class microservice that you can call from other services. And one of the nicest examples of this was a project that optimizes launch schedules for our titles. So on Friday when you go to Netflix and you see that there are many new titles, what to launch and when is actually a surprisingly hard problem. So our data scientist wrote an optimizer that optimizes the schedule. And not only that, but we have a custom UI that allows business stakeholders to ask these what-if questions. What if we launch this before that? And now, thanks to the hosting platform, we run this mini optimizer on the fly, answering to these what-if questions that, well, how the kind of the schedules would change if we change this knob. So that's Metaflow. And just to recap before I run out of time, we started with the idea that we have a very diverse set of problems. And we believe that the best way to address diverse set of problems is by having a diverse group of people with different backgrounds, with different domain expertise. And we don't require that they necessarily have a super deep software engineering background. That's easy. And with diverse people, we want to embrace the fact that we get diverse models. It's fine. You should use the best tool for the job. And then, since we have this diversity, we want to help with our infrastructure to help people build these things, and especially focusing on the parts that the data scientists don't care so much about. And then we want to remove any excuses for deploying. And then the result is that people can focus on things they care about, and then our business gets results faster than ever before. That's it. Thank you.